right, we're about to get started. So thanks for showing up to the systems track. Meg and Michael will be speaking about non-blocking synchronization. Just to give you guys some context, Maggot has been doing a lot of the work in this area. He invented block-free FIFOs, hazard pointers. So it's terrific that he's joining us to give an introduction on non-blocking synchronization. So he'll take it from there. Oh, and sorry, the videos will be available of all the talks. The videos will be available after the conference.
Thanks, Sam. Okay, so I'll talk to you about non-blocking synchronization and memory management. If you don't know anything about it, that's fine. By the end of the talk, you should be familiar with it, and we'll get to some depth that you really get a flavor of what it is like and what are the main issues are. So I will start with talking about non-blocking synchronization. I'll talk about the problem that the memory management solves in non-blocking synchronization, and then what problems are created and what solutions that are common for these kind of problems. So I'll start with an example for a signal handler case. So you have a case of a thread that that acquires a lock and is operating. Oh, thank you. So a thread acquires a lock to operate on some shared data. The scheduler decides to interrupt it to deliver a signal. So now you have the signal handler running while the main thread is blocking, or basically waiting for the signal handler to complete. The signal handler needs to acquire that lock. So now we have a situation where it is actually a deadlock. The main thread cannot run because it's waiting for the signal handler to finish. The signal handler cannot finish because it's waiting for the main thread to release the lock. So in general, we can't lose locks in signal handlers because we cannot block, we cannot have the signal handler block waiting for action by the main thread. So that's an example, motivating example for non-blocking synchronization. You can think of other cases where that's also the case, where you want to be able to kill processes asynchronously, and they might be communicating with other threads and sharing data. And if the other threads have to wait for action by that terminated process, then we have the system becomes unavailable and we have deadlock. Another case is like soft real time in like media players. You don't want to have the main thread, high priority thread, waiting for action by another thread who's lower priority and let's say descheduled, and it's not running for like let's say many milliseconds or seconds. The case I gave the example of is asynchronous signal safety. So here you can, if you use non-blocking synchronization, you can have sharing between the signal handler and the main threads. Other motivations to use non-blocking synchronization is performance. So if you have multi-programming and you have number of threads that are software threads that are higher than hardware threads, then you don't want a thread that is running to block behind a thread that is or like spinning for waiting for action by a thread that is descheduled. In other cases, you can have lower overhead for non-blocking synchronization. That's not always the case, but sometimes it's lower overhead than locking. So there are several levels of non-blocking synchronization. So the strongest is wait-free, and basically if an operation takes some finite number of steps, it will complete. So that's very strong. There's no starvation, there's no live lock, there's no deadlock. But usually these are expensive and also difficult to design. The next level is lock-free, where most practical non-blocking operations are and algorithms. basically if an operation takes a finite number of steps, you're not guaranteed that this operation will finish, but you're guaranteed that some operation in the, for the same kind of object or it will complete. So that's basically, you're guaranteed that there's no live lock, and there's no deadlock, but actually an operation may start. And for practical purposes, this is good enough for many use cases. The weakest form is obstruction-free, which is basically if you run alone, you will finish. So you can have live lock. If there are active threads, they can get in each other's way. But it's very useful in the case of like signal handler. It's good enough because you know that the main thread is not running, but then the signal handler will, if it runs alone and it's not sharing with anybody else who's also running, then it will finish. And also for the kill safety, that's also good enough to have obstruction free. Just very quickly, I will give you like, I feel what it is like to be a lock-free operation for those who are not familiar. So this is like the simplest case is a lock-free counter. So you have a counter that supports two operations, read and fetch and increment. And the structure is like an integer. So using the compare and swap operation, which basically atomically compares the value stored in memory with an expected value, if that's true, if they're equal, then it writes a new value to the memory location. If not, it returns false. So that's like we're going to use that a lot in this talk. So this is compare and swap, and you can have an implementation of read. It's basically wait free. You're just going to read this integer because it completes in one step. So there is nothing there to prevent it from completing, provided that the hardware is providing you with wait-free reads, which almost all do. For the fetch and increment operation, you can see that it's lock-free. Basically, every time you go through this loop completely, so like if any thread executes these two steps, it might not succeed. The compare and swap may fail if someone changes the value of X, but then we know that someone, if this is all if these are all the operations that are valid for this object, then we know that someone must have succeeded in the meantime if the current thread fails for the fetch and increment operation. So it is lock-free. So just a few like comments on, to clarify what non-blocking operations are about, is that they are property of operations. So it's not like the whole data structure has to be non-blocking. You could have, like, for example, there are hash tables and lists where you can have the lookup operation is wait-free, but then the updates are actually using locks. So you can mix and match, and it's all about the operations that you care about. If all the operations are, like, let's say, lock-free or wait-free, then you can say that this whole data structure is lock-free or wait-free. Some other misconceptions about non-blocking synchronization is that because it guarantees progress, it's actually somehow fair. Actually, no. I mean, not necessarily, as we saw that, like, there can be starvation for lock-free operations. So fairness is not guaranteed. You can have fair locks, but then they're not non-blocking. And another thing, of course, is like lock-free does not mean just no locks. Yeah, sure, that that's prerequisite that as long as you have irrevocable locks, they cannot be lock-free. But then you can be blocking in a different way. You can be spinning on some flag that's still blocking and not lock-free or non-blocking. What's it all about is that you can delay any number of threads, and the active threads do not have to wait for them. So that's kind of like the key property of non-blocking operations. All right. So I give you a very brief overview of what non-blocking synchronization is about, and this is kind of like the main topic of my talk is memory management. How memory management interacts with non-blocking synchronization. So I will show that it actually solves problem. It helps with eliminating some problems in non-blocking algorithms, but then it creates a lot of problems, and we have to solve these. And in a way, if you're designing a system that supports, requires and supports non-blocking synchronization, most likely memory management will be the biggest, most complicated part of that design. So I'll give you this will be a running example in this talk. So let's say we want to implement a wide compare and swap. So you don't have an operation in hardware that supports that. It's like, let's say it's multi-word that or spans multiple cache lines. So no hardware supports that. So now you want to implement that in software. So a common solution is to do a copy on write kind of implementation. Basically, you, instead of keeping the value in place, as in like this is the abstract data structure, you actually implement it by having a pointer that points to a dynamic block that holds the value, and every time you change it, you actually gonna put a new block with a new value. So this is the relatively short piece of code to do that. If you want to do this wide compare and swap, you're gonna read the pointer. You're gonna dereference that pointer and check if it matches the value that you're expecting. And if it does, then you allocate a new block and you set its value, and you try to do compare and swap to switch the pointer. So that's a regular compare and swap that is word sized. And you delete whichever block depending on the success or failure. You're saying, okay, I don't need that one of the blocks. So that's a kind of it looks like a very simple piece of code, relatively small, but it's full of problems. So you can, that's when you want to update, you want to switch the values by switching blocks. But yeah, looking at this block, it solves one problem by giving us the ability to do wide compare and swap, but then it creates, there are like 5 places in this short piece of code that are problematic or needs attention to be correct. So let's look at some of the problems that actually, going back, so I'll go through some of these problems, and I'll start with the ABA problem. So in this case, the code in red, that is what's problematic. So let's look at that kind of example here. You have thread I reading the value A from pointer P. Then you have thread I reading the value U by dereferencing by looking at block A, by dereferencing the pointer at thread. And now it says, okay, that's good. This is the expected value. So the next step will be, the next time will be allocate a new block and so on to try to do compare and swap to switch the blocks. In the meantime, you have a thread J that actually changes the value of pointer P to a block B that has the value W, different from U. And now thread J reuses block A to hold the value Z, not U. Now the value is Z in block A. And it succeeds. It's running alone. Everything is going fine for thread J, but thread I is asleep. So now it succeeds, and it sets pointer P to A again. And now thread I wakes up, and it allocates block C. That's fine. And now next step, it will it will want to do the compare and swap on the pointer P. And all what it sees is that, okay, P was pointing to A. It is, and it succeeds. The compare and swap succeeds. But then this is incorrect because it's actually block A had value Z, which means the abstract data structure had the value Z, and the compare and swap should succeed only if the value was U. So now we have incorrect outcome because the read part of compare and swap doesn't know the difference what happened in between this operation when it read and then this operation when it read again to confirm that it has the same value. So basically this happens when some thread I reads a value A from some shared variable, other threads change the value to a different value B and then change it back to A, and then the first thread wakes up and finds that the value it cannot tell if it has changed. It finds the same value, and the algorithm is dependent on the assumption that if it doesn't change, then it will be the same. The data structure hasn't changed, and the correctness depends on that. So primitives susceptible to the ABA problem are read and variants of compare and swap, like whatever compare and swap on like two independent locations, 4 independent, it doesn't matter. They all have this kind of characteristic of, as long as they are reading value and comparing it with an expected value, they would be susceptible to this problem. The interleaving of events, this kind of ABA, is necessary but not sufficient. So when when a problem happens, yes, this must happen. But then if this case happens, it doesn't mean that it doesn't mean that there will be an ABA problem. Some cases are benign. Okay, now getting to this is the classic example. This is from the early 70s. You have a pop from a LIFO list. So it's like a stack or a linked list that is LIFO. This operation is incorrect. Basically, it has the ABA problem. So what you expect to happen if there's no problem is that you read the first the pointer from the anchor. That's the first node in the list, and then you see okay, that's the next one is B. You're gonna try to do compare and swap and move the anchor to the next one, and now you have popped the first node. So again, you have a thread I that reads the value A from anchor. Thread I reads the value B from like the next pointer of A. So far so good. And then you get now the problem starts. Thread I goes to sleep or whatever, delayed, and then thread J succeeds in popping A and B. So now J succeeded in popping A and B, and the anchor is pointing to some other value C. That's fine, but then thread J comes back and pushes A back. So now we have anchor is back to the value A that thread I has seen, but then now the block B is just out there. Who knows? It might be used in some other data structure. It might have been, changed values. It's not part of the data structure anymore. So now thread I comes back and wakes up and checks that anchor is equal to A, and it succeeds, and sets the anchor to B. So this is the classic example. This is like the case where it appears in the IBM principles of operation for the mainframe system 370, and the problem was identified. So basically, you have here the data structure is corrupted. So I will talk about some solutions. This is theoretical solution. Load linked, store conditional, they do exist in some architectures like IBM Power and like SGI. I mean, but then there's also the validate operation, which doesn't exist on real systems. On real systems, they basically support just one pair of load link store conditional without interleaving or nesting. But theoretically, this is a complete solution to the ABA problem, because the definition is that load linked is like a read. Validate is basically you're saying returning a Boolean indicator that whether any other thread has written to that location since the current thread has read it using load linked. So it's a guarantee that there is no ABA problem, because if it happens, it would be detected, unlike a regular read. Similarly, for store conditional, it's doing basically validate, and if it is true that nobody has written to that location in the meantime, then it succeeds in writing a new value. Otherwise, it will detect that and get a false return value. So now when we look at this pop operation, we compare it to the previous slide. It's actually, this is correct. This is guaranteed not to have the ABA problem because it's using load link to read, and then later on doing the change, the pop using store conditional. So sometimes in the literature, the ABA solutions are presented as like load link, store conditional, validate implementations, but that's kind of a little bit too strong. So as we'll see in this example, this is like the counterpart. Well, no, not yet. Yeah, this is like, as you can see here, that the atomic add or increment using compare and swap, it doesn't matter. I mean, I could use I could read the value, let's say 1,000 here in the read part, and someone change it to like a 1,010, and then decrement it later to 1,000 again, and then my compare and swap succeeds. That's okay, no harm done. So the ABA problem is not, in this case, it's benign. In the example of push in a LIFO list, this is the counterpart of the pop that I showed in the previous slide. The push operation could encounter the ABA problem, but it's totally benign. So what happens here is that, okay, I'm reading the first what is the first node in the list, and now I'm gonna, this is the block that I'm inserting. I will make it point to it and try to change the anchor using compare and swap. So here we have like the current thread doing that. As I said, it will point to the next one, and now some other thread removes one or more nodes and then push that some node back. Well, as long as it is the correct, the A. So it has to be so this is a and then later on it changed it to some other value by popping it, and then put it back. It returns to B to A. So A, B, A. So now when this compare and swap succeeds, no harm done, because it was checking, am I looking at the old value and it's still there? Yes. So that was there was no harm done there, because that's all what I'm looking for. All right. So if we use load linked store conditional to replace the reads and the read and the compare and swap, sure, that would be correct, but then that's too strong and probably wasting performance unnecessarily. All right, another problem is the memory reclamation problem. So now we're back to our running example of wide compare and swap. And in red, what is problematic in this piece of code. So we start by having thread I reading the pointer value, let's say A, from pointer P. So now it's pointing to a block A that has the value U, but in this case it doesn't matter. It's a dynamic block, and now in the next step, it's about, now thread I is about to read the value U from that block A. It hasn't read it yet, and now we have thread J doing some operation. It replaces block A with block B, and actually, let's say it wants to return. It's done with that block. It doesn't need that block anymore, and returns it to the OS or unmaps it. Now thread I wakes up, and the next step for it. It's about to dereference or to read the contents of block A. What will happen? It will have an access violation and crash. So basically, the memory reclamation problem is that we have a thread who reads a pointer to a dynamic memory location or dynamic block. Another thread J removes that block from the structure and frees it or reuses it, and then the first thread dereferences the pointer and access a freed or a block or a block that has different semantics that it was expecting. So what happens here, as I showed, it can have access violation by accessing unmapped memory. It can also return incorrect result because that block was used somewhere else and it just happens to hold a different value, and the original thread is unaware of that and returns incorrect result. Or of course, if it is writing to it, it could corrupt some other location that just happens to allocate that block or that piece of memory. It's like that. The block might not be intact anymore. It might have been freed and reallocated as part of a different structure. So this is the memory reclamation problem, and it boils down to saying how can I reclaim dynamic memory blocks that are removed from non-blocking data structures while guaranteed that no thread will have access to a freed block. Like when it is safe to free a removed block, as in I'm guaranteed that nobody else will be able to access it. And this is quite difficult because as a thread, I cannot wait for as a thread who's removing a block, I cannot wait for someone else to finish reading what they are intending to read. And as a reader or someone who's traversing a dynamic structure, I cannot guarantee to say, wait, don't remove it because I'm about to read it. So for non-blocking operations, we cannot wait for each other. So that's how we need to solve the problem in a way that actually gives us this guarantee without expecting any waiting. So quickly, just to say that the relation of the memory reclamation to there are very different problems. One of them applies to dynamic memory. The other ABA can apply to there's no dynamic memory and still happens. But then it's basically the relation between them is that solving the memory reclamation problem often solves the ABA problem. In the same time, it just it can come for free to get an ABA solution. Another thing is that a complete ABA solution can be constructed by using memory reclamation solutions. I mean, even if you have, let's say, static structure, you could use an extra level of indirection to construct a complete solution to the ABA problem. Okay, so this is the classic solution. Actually, I found it in a patent application from IBM that was filed in 1973. for the ABM tag, so the ABA tags. So basically, they had that. What they had is the example for the pop operation that I mentioned earlier. Without the tag, it was incorrect using compare and swap. But then using compare and swap double on double word, you can prevent this problem. So basically, you would have the anchor would have a pointer value, and contiguous to it in an aligned block, you have an integer value. It's basically a counter of how many pops happened in this structure. So in this case, you have like, let's go through this again. Thread I reading the value A, but then attached with it is a tag. In this case, the value is 100 from anchor. Then it reads B again from the next pointer of A. That's fine. Now thread J pops A and B. So it's doing two pops. I'll just do them in one step here, which means that the value is updated from 100 to 102. And now thread J comes back and pushes A again, and now we have, okay, the anchor is A, but then the tag is different, and thread I comes back to do the compare and swap. It finds the pointer equal to A. That was expected, but then the tag has changed, and the compare and swap fails as it should, and the problem is prevented. Okay, so this has been used in non-blocking data structures for more than 20 years as the main solution for the ABA problem. And it has, of course, it's very simple. It's weight-free. There is no, it's just part of reading and updating the pointer. And it has relatively low overhead. But then the cons, it really complicates it complicates the memory reclamation. It becomes, the tag becomes part of the semantics of fields of dynamic structures. And now what do we do? How do we free that memory block and reuse it arbitrarily if some of the fields have semantics that have to be maintained indefinitely, like the tag in this ABA solution? Another thing is, of course, it requires a compare and swap or read and compare swap that are wider than single word. And also there's a theoretical chance of wraparound, especially if the tag size is small. Okay, so now looking at these problems and solutions and say, how does garbage collection help? Let's just assume that we have ideal garbage collector that just once a dynamic block doesn't have any references to it, it is freed instantaneously, and it doesn't have any overhead. So it helps by preventing the memory reclamation problem, of course, that's by definition, but also it helps in prevent the ABA problem if we follow certain rules. So it's not an automatic solution, but if we follow the rules, then it provides a solution for free. If the ABA problem involves only the pointers to dynamic blocks, then okay, that has to be a condition. And then the contents of the dynamic block, we do not change it after being removed from the non-blocking structure. And then once it is removed, we do not insert it back until it goes through a reclamation cycle. So you cannot just remove and put it back. Then we're not benefiting from the guarantees of the garbage collector. So what if we don't meet this solution, these requirements? Well, okay, yeah, this pop operation is correct. I mean, I showed this code before. It was incorrect in showing both the ABA problem and the memory reclamation problem without garbage collection. But now, with garbage collection, it's correct. So it really simplifies things. Now, what do we do if we we cannot keep memory block, dynamic blocks not reinserted. So I hope you can see that basically, so now we have a pointer, we have a dynamic block that actually we want to be able to, to move from one structure to another and back. So a level of indirection would solve this problem. Of course, it has overheads, but then it would provide us with a complete solution. So basically, this auxiliary block, which is barely one word, one pointer, it has to follow this life cycle. It has to respect that, while the main block can be reinserted immediately, but then, of course, with a new auxiliary block. Okay, so I talked about the ABA problem. I talked about memory reclamation sometimes for free solves the ABA problem. So now I'll talk about like three different categories of solutions of the memory reclamation problem. They have different kind of characteristics and techniques, and they actually might not they apply to different algorithms. So there is per block reference counting. This is very fine grained. Basically, every time I'm creating a reference to a dynamic block, I actually atomically increment a reference counter, and every time I'm releasing that reference, I decrement that counter. So it is quite it has high overhead for doing the operations. So the pros, it's the tightest. Compared to ideal garbage collection, this is the next thing that is basically, if you have n threads, you can only have n collectible blocks that are not freed yet. It is lock free, but it's not weight free usually, unless you have, because it usually involves compare and swap. The cons are that readers actually interfere with each other. So now I'm incrementing the counter. Someone else incrementing the counter. They can get in each other way. Also, the writer starvation. So you can have a writer who's about to, let's say, let's say push an item to a list, and then there are readers who are kind of traversing the list searching for that item, and they keep decrementing the reference counter and get in the way of the writer. So that's a disadvantage that other techniques don't have. Another class of solutions is epoch-based solutions, and one example is RCU, read copy update, which is very heavily used in the Linux kernel. It has like thousands of uses there, and basically it's like you have threads. If they remove an item, they hang on to it, don't free it until you reach an quiescent state for the other threads. So you can say, okay, we reach a point where actually we know that nobody else is holding a reference to that block, and then we can have free all the blocks that we collected during this epoch, and we'll do that safely. So the advantage is that it has very fast reading. Basically, reading is not incurring any overhead. It's not doing anything extra per traversal, per node. It pays us some price in the beginning to set up. Like say, okay, I'm participating in this epoch-based technique, and the readers do not interfere with each other and do not interfere with writers. They are just reading. The cons is that if you might end up collecting a lot of blocks that are not freed and might run out of memory. So basically, it is not effectively absolutely non-blocking, and there is no bound on the memory that you could collect and not free until you wait for the end of the epoch. It is very useful for cases where you have read mostly and infrequent updates. Okay, another solution is hazard pointers. Basically, it's a single, each hazard pointer is a single writer, multi-reader pointer. So each one has an owner. The owner thread is the one that can write to it. And by setting a hazard pointer to a value pointing to a dynamic block is basically telling other threads that if you happen to remove that block after I've set my hazard pointer, do not free it until I change the value of my hazard pointer. That's kind of basically the message. And surprisingly, it's very simple technique. Basically, looking back at our pop example, so the extra code here is that so after you read the pointer value from anchor, you actually set a hazard pointer to it, and that actually write to the hazard pointer doesn't even have to be atomic. You could do it, bit by bit in any order, but then you have to, after that, you have to recheck that the anchor still has value. Why are you doing that? Because what if you set the hazard pointer, but actually it already has been removed by someone else, and someone else has checked my hazard pointer and found it different value? Then they would be able to free that block. So I check again because I need to make sure that it is there. So even if someone removed it and put it back, that's okay, as long as I check that it's already there and I already set my hazard pointer. From that point on, I am guaranteed that it will still be there until I change my hazard pointer. So basically, it is safe. That the two problems that we were having here with this operation is that dereferencing that pointer, that's safe because we know it's there, it's not freed. And then also, for this example, the ABA problem will not happen because we know that that block will not be put back in the data structure. So that's basically what the reader does, the thread that is traversing. That's all what it does. On the flip side, this is the remover. The remover thread, all what it needs is to, for performance purposes, it can accumulate a bounded number of blocks that is removed. So it doesn't have to do this every time, but it can, collect a bunch of them. And all what it needs is to read the active hazard pointers of the traversers. And that these reads don't even have to be atomic. Just, read them bit by bit in any order. It doesn't matter. And this is the only shared operation that the remover needs to do. The rest is to organize it in some fast search data structure, and then match it with the bunch of blocks that it has collected. And so now we know that there is a bound on that. There's a bounded number of hazard pointers in the system, and only that up to that much or that many blocks will not be freed. But all the rest guarantee that they will be free. So, and that's all. That's all what it involves. So the pros is that it's lock free. It's actually amenable to being weight free. So sometimes, if you find that the value has changed when a traverser, they can just take the path, the weight free path, and say, okay, that they don't need to go back and read again. So it depends on the algorithm. It might be it could be weight free, while reference counting actually can be if you don't have in certain primitives that are not common, it will have to be lock free. Um, no atomic instructions involved, but there is a memory barrier there because you're writing and then reading, and you need to guarantee that order. It has constant expected time per reclaimed block and no reader interference. So that's readers don't get each other way, and the writer can proceed with unimpeded. The cons, of course, it has overhead of like this. You're doing this in every traversal step, and there is a worst case of product of the number of removers times the number of traversers. They might be the same threads, but that's kind of the traversers that the ones who own um, hazard pointers. The removers are the ones who are removing blocks and have to check the hazard pointers. So you might end up with a quadratic number of blocks that are not reclaimed. Reference counting has a linear number, but it has its problems, and it gets in the way of memory reclamation. It's good for reuse. Epoch-based, it's unbounded. Here you have it's completely lock-free, and it's bounded number of blocks, and it doesn't have the disadvantages of reader interference. So it is kind of that's kind of by covering these categories, you can see the trade-offs among them, and depending on the case, you can decide what is really the best technique to use. Now, okay, we have. So quickly, I'll go through this. Like there's kind of a pitfall in designing non-blocking algorithms. Is that you could say, well, for simplicity, I'll just keep some pointers, valid even when the blocks are removed from the structure. So this can be like simple, but leads to problems. And I give you an example as a simple linked list traversal. Basically, when someone removes a node, they are not going to nullify that pointer. They'll keep the pointer intact. So now we have the thread that it was traversing, and now it went to sleep. And another thread comes along and actually it removes the node that it's pointing to. But then because the algorithm requires to keep like let's say it's using reference counting, or so it depends on the technique, it might require that. Hazard pointers would allow to nullify, but reference counting would require that you depending on the algorithm, actually not the technique, not always, but some algorithms require that you keep that pointer intact, this one. Now it removes another node and removes another node, and I've seen it in practice. It can be, within in no time you can get like tens of thousands of nodes that are just accumulating, and you say I never expected this data structure to get more than 100 items. How come I just gave it 100,000 nodes and still ran out of memory because of this problem? So this is just something to be aware of. Sometimes it's worth it, sometimes it's not. So to avoid this problem, you could, of course, nullify the pointers. So it solves the problem, but then, of course, it complicates things for the sleeping threads, the thread. Now, when it wakes up, it cannot just go along, like, continue what it was doing without any problem. Now it has to be aware, okay, it has to compare, am I still there? Am I still part of this data structure? It has to check the previous pointer. And in this case, it will find out that, yeah, okay, it's looking at a node that was deleted, and it will have to, let's say, for example, start over from the beginning. So there are trade-offs there. So in general, the persistent problem, pointer problem, they actually require, like they have restrictions. Basically, they cannot have like a reuse. Like you cannot just like take a node and then put it back somewhere else, because actually you do have to keep the next pointer valid. So it is inconsistent with that kind of use. It cannot use hazard pointers because Basically, the hazard pointer allow reclamation that of blocks that are indirectly pointed to by that block. So if you rely on holding that node, and then it will prevent the reclamation of all what follows it, you cannot do that with hazard pointers. So it would require you to use a technique like garbage collection or reference counting or epoch based. So it limits your options if you do that. Okay, I'll get through this. This is the issue of allocation and deallocation. So now, for many decades we had like from the early 70s to the early 2000s, or all what we had is, okay, we can just reinsert blocks. We can use the tags to prevent the ABA problem, but we cannot reclaim data blocks. Then there were epoch-based solutions came along, and we say we can reclaim blocks, but only at the end of an epoch, which is not quite non-blocking, because you can accumulate a lot. So now we solved these problems, and now it became, okay, now we need to have malloc and free that we actually can use. Now we know how it is safe, when it is safe to free a block, but we didn't have algorithms to say, now we can have a general purpose allocator for malloc and free. So I know that time is, how much time? Probably we have like,
We're gonna wrap up pretty soon.
yeah, okay. All right, so this is like the design is basically using super blocks to have like equal size blocks in an array, and then to facilitate non-blocking operations, is actually we're keeping the descriptor, which is like a few words in a separate structure. So that descriptor we can allocate them and deallocate them separately from the bulk of the memory, which is in super blocks. And it's basically like so there are levels of heaps. So there are heaps that are accessed by you can have multiple heaps that are accessed by by different groups of threads, and then you have super blocks that are completely allocated. They are not owned by any structure. If they're partially allocated and not owned by any heap, they would be in a global partial structure. So all these have to be managed in a lock-free manner. So allocation, basically the path is, there's a fast path saying, I'm a thread, where's my heap? It doesn't have, I might be sharing with other threads, but we're unlikely to collide if we have so many other heaps for other threads to use. So now I look at my heap and see that, okay, there is an active super block and it has space. Then I can allocate from it, and we're done. That's the fast path. If I don't find an active super block, I have to allocate from the partial list, again in a lock-free manner. If not, then I'll have to create a new one and make it active. So it's a more complicated algorithm, so I cannot really show you code on one slide, but I'll show you the common case. So this is like the fast path. So you have a super block. I want to allocate a new block, and this is the descriptor. This is the heap header that is pointing to the descriptor of that super block. So there are lots of reads. First I'm reading the header, then I'm reading the descriptor state, and then I go to recheck the header, because I really, it's part of the algorithm, and then I read the next pointer of the head of the list. So the head of the list is block 5, and the next pointer will be pointing to 6. And now I do a compare and swap that will change the state to pop that block from the linked list, and we're done. So that's the fast path. For the allocation, it's kind of a few steps, as in the fast path is just I push the free block in the super block. If it is not full or empty, then then nothing. I mean, that's it. I'm done with the operation. If I'm happening to be putting the first block in an empty super block, then I have a responsibility to make it a partial block. If I'm pushing the last block in a super block that becomes completely free, then I have a responsibility to make it free. So looking here, again, this is the common case only. I read the descriptor because now I don't need to go to the heap. I know the descriptor from the block. Then I read the next pointer. So now I have of the freed block, and I set it to the top of the linked list. So this is the first one, and then I do a compare and swap to change the state, and here we go. We're done with the operation. So it's one compare and swap. Okay, very briefly, this is the almost last slide. How you are building a non-blocking algorithm or the structure, and how do you deal with memory management? How to think about it? So the first is abstract away memory management and focus on the core algorithm. So how to do that? You don't want to think that you just have ideal garbage collector. That's not good. You have to think that you have memory management that will you will nullify pointers. So for example, you have a perfect garbage collector, but you have to be explicit about the allocation. So you cannot just say it will be collected. No, you know, okay, this is the time when I remove the block. Because there are algorithms that don't know. Like they can have multiple pointers and they don't know when it was really removed. So you have to be able to think that it's, I could put explicit allocation, the allocation here. For the ABA problem, don't think load link store conditional. They're too restrictive. Just think about compare and swap that is can just avoid the ABA from happening. It's like as if you control the scheduler and the scheduler will not let it happen. So now, after you design the core algorithm with these assumptions, then you start looking at the options for both problems. And because they are intertwined, they actually, one solution might solve the other, and you don't have to pay the overhead twice. So that's kind of like, these are like steps to consider for designing non-blocking algorithms with memory management issues. In conclusion, I talked about non-blocking synchronization. They are mostly useful in applications where active threads cannot or prefer not to block behind threads that are delayed for whatever reason, and sometimes for performance where it's actually faster to do that than to acquire a lock and release a lock. Memory management is usually the most complicated part of designing non-blocking algorithms, and it solves problems and creates problems, and we went through these. And I should point out that memory reclamation and the ABA problem, they occur in concurrent in optimistic concurrency. So you might not need a non-blocking synchronization, but actually you might be designing optimistic algorithm where you, let's say, you're traversing a tree and only lock at the leaves of the tree when you're about to do updates. Now you have these traversers are just reading, and if someone removes something in their way, they will have memory reclamation problem. They'll have ABA problem also if they are double checking something. So the problems I talked about are not only for non-blocking synchronization. Solutions can be useful there, but then the solutions that I talked about were restricted by saying they have to be non-blocking. If you don't care about that, then actually, let's say you use epoch-based solution like RCU, where
you know you can be using locks combined with optimistic concurrency, and you say, okay, that I can wait for the readers to finish reading, to finish an epoch, and then free my memory. So I mean, yeah, you can look at these as like tools in your toolbox. It's not like, you know, binary. You have to use all or none. They're useful in multiple contexts. Well, thank you. And